In this video, we're going to take a look at another comparison test to determine when series converge or diverge. Now, this test is called the direct comparison test. So this test makes the following statement. If you have two sequences, AN and BN, and the ANs are bigger than 0 and less than or equal to the BNs for all n. It doesn't really need to be true for all n, it just needs to be true for n sufficiently large. So in other words, for n bigger than or equal to some capital N, like as long as this is true for little n being bigger than 1,000,000, say 1,000,000 to infinity. Okay, it doesn't need to be true for every single n, just for all n bigger than some fixed number. Then it makes this statement. If the series involving the Bn terms converge, then so does the series involving the An terms. On the other hand, if the series involving the An terms diverges, then the series involving the Bn terms diverges as well. This should be pretty clear that why this is true. So for example, with number 1, we're saying suppose the series involving the BNs converge. Well, all of the ANs are smaller than the BNs, right? So if this series exists, then certainly this series will exist as well, or converge, because each of these terms is smaller than all of the terms involving the B's. So it makes sense that the A's should converge. On the other hand, if the series involving the ANs diverges, then the series of the BN terms must also diverge. That should make sense, because if this series diverges, goes to infinity, then certainly this series should also diverge, because all of the B terms are larger than all of the A terms. And the series involving the A terms goes to infinity, so certainly the series involving the B terms should also go to infinity. So this makes sense when you think about it. Now, let's take a look at a few examples of how we actually use this test. Now, the only problem with this test is when we look at the examples, you sort of have to, you want to decide, am I in case 1 here or case 2? So you sort of have to have a feeling for, does my series converge or diverge to start? You have to sort of have a good idea whether your series will converge or diverge. And then you can use either case 1 or 2 to prove that. So for example, if you think your series converges, then what you want to do, then your series would involve the AN terms. So suppose you think your series converges. Then you want to find another sequence of B's which are slightly larger than all of your A's, in which the series involving the B's converges. And then that will prove that your series involving the A's converges as well. On the other hand, if you think your series, let's say your series involving the Bn terms, if you have a feeling that your series diverges, then you're actually sitting here and you want to find another sequence of AN terms in which the series of the AN terms diverges, then that will prove that your series diverges. So you sort of have to have a feeling, am I going to be in case 1 or case 2? That's going to determine whether your series, whether you should think of your series as being the ANs or the BNs. We'll take a look at some examples to clear this up. Now we'll also see later on, and we're going to come across another test called the limit comparison test. That sort of supersedes this direct comparison test, it does basically the same thing, and we'll see that it's actually easier to use. So you'll probably prefer to use the limit comparison test anyway. But let's take a look at a few examples. And direct comparison is a useful test to have. We use it to prove some results later on. So it is a useful test, even though in practice, when you're actually doing problems, you'll probably prefer to use the limit comparison test. It's a little bit easier. So let's take a look at this example. Let's determine if this series converges or diverges. All right. Now, we have to sort of decide, do we think this converges or diverges? Well, if we look at the an terms right here, 1 over 2 plus 3 to the n power, notice that for n sufficiently large, this 3 to the n power becomes so dominant that the 2 really doesn't matter after a while. And this is sort of behaving like 1 over 3 to the n power. And we know that the sum from 1 to infinity, 1 over 3, if we write it like this is a geometric series, which actually does converge. So we have a feeling that this is going to converge. All right, so what we have to do then, if it converges, then we're actually in case 1 in our theorem. So we want to try to find, so we're going to look at these as being the ANs, and we're going to try to find terms BN that are a little bit bigger than the ANs, in which the summation of the BNs converges. So this is what we're going to try to do. We're going to try to find these BNs, which are a little bigger, in which the series involving the BNs also converges. And then that will prove that the series involving the ANs converges, so that will prove that this series up here converges. Okay, so what we have to do is we have to start out with 1 over 2 plus 3 to the n, and try to find a sequence which is a little bigger than this one. All right, now to make this fraction larger, what we need to do is actually make the denominator a little bit smaller. See, if we make the denominator smaller, we will actually make this bigger. So this one's actually pretty easy. All we have to do is just get rid of the 2. So you see, 1 over 3 to the n power is actually bigger than 1 over 2 plus 3 to the n, because over here the denominator is a little larger. So certainly this is going to be true. Another way to see that this is true, if you're not convinced, is to just cross multiply. So multiply each side by 3 to the n, move this over here, move the 2 plus 3 to the n over here, and you get. So certainly these two statements are equivalent, and so, because certainly 2 plus 3 to the n is bigger than or equal to 3 to the n, and these two statements are equivalent, so certainly this one is true. Okay. And so now, note that the series of 1 over 3 to the n from 1 to infinity equals the sum from 1 to infinity of 1 over 3 to the nth power, like that. In fact, this exists, it converges, because it is a geometric series. In fact, in this case, we actually know what it even converges to. If you remember now, we're actually starting at 1 down here. So since we're starting at 1, this series actually converges to 1/3 over 1 minus 1/3, r over 1 minus r. And the reason we have it like this is because we're starting at 1, remember. If we started at 0, it would just be 1 over 1 minus 1/3 if we started at 0. Okay, That was a result that we had in a previous lesson. And so, this is equal to 1/3 over 2/3. So 1/3 over 2/3, and that's just equal to 1/2, which of course exists. Okay, so this converges, and the 1 over 3 to the n is bigger than or equal to 1 over 2 plus 3 to the n, so therefore by direct comparison, this series converges. All right, so quickly to summarize, we had a feeling that this series converged. So we were in case 1 in the theorem that we looked at. And so we wanted to try to find some bn's that were a little larger than our an terms. Our an's were these up here. And we wanted to find bn's which were a little larger, in which the series involving the bn's converged. So we found them to be 1 over 3 to the n, the bn's right here. And this is the series involving these terms is a geometric series which converges. Therefore, the series involving these terms converges. Let's take a look at another example. How about this one? Determine if this series converges or diverges. All right. Well, considering our terms here, n cubed, you notice that for n sufficiently large, in the denominator the n to the 4th power dominates n squared plus 1. So we can basically sort of think of throwing these terms away, and for n sufficiently large, this fraction here will be behaving like n cubed over n to the 4th, which is equal to 1 over n. Now the sum of 1 over n by the p-series test, notice this is n to the 1 power here. So by the p-series test, this will diverge because the p is equal to 1 in this case. And so this series diverges. So we have a feeling that this series here will diverge. All right, so what that means is we need to think of these terms as being the bn's now. So these are equal to the bn's. We're in case 2 now in that theorem that we looked at, and so we want to find a sequence of the an's, which are a little smaller than the bn's and also bigger than 0, in which the series involving the an's diverges. Okay, so that's what we're going to try to do. We're going to try to find the an's, which are a little smaller than our terms up here, thinking of these as being the b's, in which the series involving the an's diverges. And the reason we're doing this is because we have a feeling that this series diverges because of what we discussed over here. All right, so we need to start out with the n cubed plus n squared plus 1. And we need to make it a little bit smaller. And we'd like to end up with something that looks like 1 over n when we do this. All right, now to make this a little bit smaller, what we want to do is make the bottom, the denominator, a little larger. Okay, so what we're going to do is this. We're going to change the n squared into an n to the 4th. Notice for n going from 1 to infinity, if I take an integer bigger than or equal to 1, raise it to the 4th power, that's certainly going to be bigger than if I squared it, right? So I'm going to make the bottom a little larger by replacing the n squared with an n to the 4th. So this statement is certainly true. And I'm also going to replace the number 1 with an n to the 4th. Certainly n to the 4th is bigger than or equal to 1 for n going from 1 to infinity. So I'm going to replace it with an n to the 4th as well. Alright, so I made the denominator here much larger, so I've made my overall fraction smaller. And the reason I chose the n to the fourth, you see, is because now these are all the same term. I can add them all up and I get we get 1 over 3 times n. And this looks like 1 over n, right? So now note, if we look at the summation 1 over 3 to the n, okay, I can just move that 1/3 out. Let's say this goes from 1 to infinity. Okay, now we see that this diverges, including the 1/3 as well. So this diverges by the p-series test, and therefore the original series that we started with must diverge because all of the terms here, n cubed over n to the fourth plus n squared plus 1, are bigger than 1 over 3 times n. And this series diverges, so this one must diverge, and that's what we've concluded. All right, let's take a look at one more. How about this one? All right, so if we're going to use direct comparison, we have to have a feeling for whether our series converges or diverges. Well, if we look at, we see that as n gets really large, if we look at this term here, we see the 2 really doesn't matter right after a while. So this is going to be behaving like 1 over the square root of n, which is 1 over n to the 1/2 power. And we know that the summation of 1 over n to the 1/2, here the p is equal to 1/2, which is of course less than 1, so this series will diverge. Remember, it only converges for p strictly larger than 1. So here the p is less than or equal to 1, and so it diverges. So we have to think of these then as being the bn terms. So we want to try to find some an's that are a little smaller than the bn terms. Okay, well, so we want to start out with 1 over 2 plus root n, and we want to try to make this a little bit smaller, so we're going to try to recover the an terms. So we see that we can replace the 2 with the square root of n. Certainly the square root of n will be larger than 2. Now technically that's only true for n bigger than or equal to 4, but that's okay, just as long as it's true for n sufficiently large. And so by replacing the 2 with the square root of n, we will make the denominator larger, and so we'll make the term smaller over here. So this will be bigger than or equal to 1 over root n plus root n. And once again, technically that's only for n bigger than or equal to 4, but that's okay, as long as it's true for n sufficiently large. And this is equal to 1 over 2 root n. And now note that the summation of 1 over 2 root n from 1 to infinity equals 1 over 1/2 times the summation, and this term right here diverges because the p is 1/2 in this case. And so this series right here will diverge, and these are the series of the an terms. So this, and the an's are the 1 over 2 root n. So the series involving the an's diverges, therefore the series involving the bn's must diverge also, and the bn's were these. And we chose these to be the BNs because we had a feeling that this series diverged to start with. So therefore, by direct comparison, we have concluded that and there we go. Alright, so that concludes our discussion about the direct comparison test.